In this video, I'm going to go over the rest of our notes from 10.1 System of Linear Equations, so you'll want to get those out. That was sort of a yellow sheet of paper that we had. We did example 1 and example 2 in class, but I'm going to go ahead and go through them in this video because I think a couple people were absent, or maybe you went through it and you just want to look at them again. So if you're comfortable with example 1 and example 2, then you could skip ahead in the video to the point where I go over exploration 1. Alright, so example 1 says to solve the system by substitution. So when you're using substitution, you want to get one of the variables by itself, and it will work no matter what variable you get by itself. We could get this x by itself, or this y, or this x, or this y. My advice is always to get the variable that has a coefficient of 1 or -1 by itself. That way you're going to avoid fractions. So I am going to isolate this y. I think what I'll do is minus the 13 on both sides and add the y to this side, and that's going to give me 2x minus 13 equals y. Alright, that's the first step. Now comes the actual substitution. Since y is equivalent to 2x minus 13, I can go to the other equation. It has to be the other equation. I used to get in trouble all the time. I would plug this back into the same equation, and then everything drops out. You get 0 equals 0, and I'd get so confused. Why is everything gone? You have to plug it into the other equation where the y is. Okay, so let's see what we get. So I'm going to just bring this down. This negative 4x stays the same. Minus 9, that stays the same. Now instead of y, I'm going to write 2x minus 13. Since 2x minus 13 is a binomial, I have to use the parentheses here. And that's my y value right there. Instead of 9 times y, 9 times 2x minus 13. So what we have now is we have an equation in one variable. Now we can solve this. Okay, so we do that, distribute, let's see, that's positive 117, combine like terms. We'll subtract the 117 over. So what does that give me? Negative 110. Alright, divide both sides by negative 22, and we get positive 5. Alright, when we're solving a system, we have to find both the value of x and the value of y that make the equation true. So we have x is 5. Now we have to find y. So we're going to take this 5 and we can plug it back into either equation. Anywhere there's an x, we could plug it in here. We could plug it in here. This looks like the easiest. Oh, I need to turn off that speaker. So if I plug 5 in for x, I get 10 take away 13, which is negative 3. Okay, so let's check these answers real quick. You can always check your answers by plugging in 5 and negative 3 into each equation. So the first equation, 2 times x, which is 5, minus y, which is negative 3. Does that equal 13? 10 plus 3 is 13. That looks good. Second equation, I have negative 4 times x, which is 5, minus 9 times y, which is negative 3. That's supposed to be 7. Negative 20 plus 27 is 7. Good. All right, so that is the solution. And we could also write the solution as an ordered pair, 5, negative 3. All right, the next one we did elimination. So with elimination, you want to add the two equations together and get one of the variables to drop out. Now this is a little tougher example with the fractions. So I think that, there's multiple ways to do this, but I think I'll take a step and just clear the fractions of this first. I did it a little bit different in class, but that's okay. So I have a 2 and an 8 here. I'm going to multiply by the least common denominator of 8. Alright, so 8 times 3 is 24, divided by 2 is 12. Minus, okay, 8 times y divided by 8, that's going to be 1, y, right, equals negative 1. And then I'll just write this down here. All right, so that got rid of the fractions. That was kind of nice. Now, what I want to do is add these two equations together and get the variables to drop, one of the variables to drop out. So if I want this 3y to drop out, I need a 3 here. This is a little bit tougher. I'd have to find the least common denominator between 12 and 16. So I'm going to do the easier one, and I'm going to get the y's to drop out by multiplying this equation by 3. So that's going to give me 12x minus 3y equals negative 3, and then I'll bring this equation over. And you'll see when we add these two equations together, 12x plus 16x is 28x. Actually, I made a little mistake here. Let's go back, right back here. Easy to fix. Maybe you caught it. If you caught it, congratulations. When I multiplied all these by 8, I need to take this 8 times this negative 1 as well. Okay, so this should actually be a negative 8. Okay, that's going to change this. So when I take negative 8 times 3, I get negative 24. All right, let's see if this is a little nicer now. So when I add these two together, I get 4052. All right, I'm sorry, guys. I'm going to have to slow down. I think I'm trying to go too fast here. I see another place here that I didn't distribute to everything. 3 times 12, I didn't distribute there. All right, slow down, Christopher. We'll just slow down. We'll get it. Actually, you've probably had this experience yourself where you make mistakes and try to figure out why. Okay, so do we do this? We did that. We did that. Let's see, is this going to work out nice? I know this comes out to be nice, so, oh, this looks better. So 4052. All right, sorry about that. I'm going to slow down here. So divide by 52, we get negative 1. All right, so now we can take the negative 1 and plug that back in to find y. And it doesn't matter which equation. You could plug it in for this x, this x, this x, or this x. I'll just do it here because it's a nice spot on my screen. All right, so 16 times negative 1 plus 3 times y equals negative 28. So that's negative 16, which means we're going to have to add 16 to both sides. So we get 3y equals negative 12, divide by 3, and we get y is negative 4. All right, so our answer we could write as an ordered pair like that. And you could check both of those, and those should work. All right, exploration 1 says, suppose you're interested in buying a new car. You have narrowed it down to 2 cars, car A and car B. Car A sells for $24,200 and gets 51 miles per gallon. Car B sells for $16,800 but gets only 37 miles per gallon. Assuming all other variables to be the same and the cost of a gallon of gas to be $3.34 per gallon, explore the cost of the car plus gas as a function of the miles driven. So the first thing we're being asked to do is complete the tables below, then write a linear function to model the cost involved with car A and car B as a function of the number of miles driven. All right, so let's start with car A. And we're trying to figure out how much it's going to cost to drive car A. Well, it's going to cost the cost of the car plus the cost of the gas. And we already know the cost of the car. The cost of the car is $24,200. All right, if you haven't already done this one, maybe pause it for a second and think about how you'd figure out the cost of the gas, and then we'll go over it. All right, so the cost of the gas, of course, depends on how many miles per gallon. The more miles per gallon you get, the less you have to pay for gas. So we're writing this as a function of the miles driven. So however many miles I drive, let's say I drive, we're supposed to figure it out for this chart here. So if I drive 51 miles and I get 51 miles per gallon, that means I only have to buy 1 gallon, right? And 1 gallon costs $3.34. So if we add that together, you get 24,200 basically plus $3.34 is going to be $24,203.34. And you kind of notice these numbers are picked nicely. What if I drive 102 miles? Well, I'm going to get 51 miles per gallon, so that's going to mean I have to buy 2 gallons of gas at $3.34. So basically 2 gallons times 334 plus 24,200. And then we'll get that number. And the next number is 153, which you'll notice is 3 gallons of gas, and multiplied by the cost of gas, $3.34. So if we figure out those numbers, just punch them into our calculator or add another $3.34 for each of these. 24,206.68, 24,210.02. So we can kind of see what's happening here. Hopefully you can see the general formula. Let's go to car B. Car B is going to be a similar situation, except the cost of car B is $16,800. If I drive 37 miles, and I get 37 miles per gallon, it's going to cost me another $3.34. And then you'll notice the next number they give us is 74, which happens to be 2 gallons of gas because I'm getting 37 miles per gallon. And then 111 divided by 37 would mean 3 gallons of gas at $3.34 a piece. All right, so we'll just keep adding $3.34. So hopefully you can see this is linear because we're adding a constant amount for every 37 miles driven in this case. So it'd be 668, similar to what's going on over here, 16,810.02. All right, so hopefully you can see the general formula. If you haven't already written it down, maybe pause it and write down the general formula. Okay, so as a function, did they tell me what to see? Okay, so I'm doing the cost as a function of miles. For car A is going to cost me $24,200 plus however many miles I drive divided by 51. That tells me how many gallons of gas I have to buy. Multiply that by $3.34 a gallon. For car B, the cost as a function of miles is $16,800 plus however many miles I drive divided by 37. That'll tell me how many gallons I have to buy times $3.34. All right, so now it says use the equations above to write a system of equations and solve by either substitution or elimination. Describe why you picked one method over the other and the advantages of using each method. Describe what your solution means and how this would help you determine which car to buy. So this is our system right here, our two equations. And notice they're both basically solved for y. C of m is just another way to write y. So the easiest thing to do is going to be substitution, right? Since this is the cost of car A and this is the cost of car B, we can set those costs equal to each other to find the break-even point. Okay, let's keep my color coordination going here. So with my blue pen, this is the cost, the y value, the cost of car B. Let's write this as 334m over 37, just as one fraction. And I want to know, when does that equal the cost of car A? Now this is a little bit of a weird equation to solve, and because of the fractions and decimals, but it's not too bad. Let's start off by getting all of our constant terms on one side and all of our m terms on the other side. So I'm going to move this over here, 16,800, and then we'll move this fraction over here, okay? I'll just write it like that. So I'm just going to write it out on this side, and then we'll talk about how to deal with this. Of course, we could just use our calculator, but so I've got that minus 3.34m over 51 because I moved this term over here. And then if I subtract those two numbers, I get 7,400. Now you could just use your calculator and punch this divided by this minus this divided by this to combine your terms together. That's probably the easiest way to do it. So let's go ahead and do that. So you're just going to punch in 3.34 divided by 37 minus 3.34 divided by 51, and you get a decimal. I'm just going to write down the first 5 places there, but you might keep it on your calculator so when you divide, you're going to divide by this decimal number. You have the best approximation divided by 0.02478, and we get 298,627. All right, and this is miles. So we'd have to drive almost 300,000 miles in order for these costs to be equal. And we're only comparing two costs here, right? The cost of the car and miles. There's other costs, maintenance costs and things that go with cars. But if you're thinking about, hey, I'm going to buy this car because it gets more miles per gallon, so I'm going to save money. It costs $24,000. Or I could buy the cheaper car, the less expensive car, but I'm going to have to pay more for gas because I only get 37 miles per gallon. Well, if you bought the more expensive car, you're going to be paying more for that more expensive car than you would have for the less expensive car until you hit almost 300,000 miles. Okay, so if cost is your only concern here, then the cheaper car would be the better deal. Now, if you're worried about the environment and gas and all that stuff, you know, maybe you'd go with the one that gets more miles per gallon, so you're using less gas. It's kind of interesting to look at these, the graph. So here's the decimals graph of these two functions. So if I graph these two functions, here's my more expensive car. Of course, it's more expensive when I first buy it, but because of the cost of gas, that expense is getting closer and closer until there's my break-even point. So when I'm close to 300,000 miles, I will have spent close to $44,000 combined between the cost of the car and the gas. And then at that point, then the more expensive, initially more expensive car would become less expensive if you're just thinking about cost and gas. All right, let's go to the next example. So in this example, we're going to solve by graphing, and we could use decimals and just punch those in, but let's practice our graphing, and we're going to see something a little different here. So this will be a good chance to practice 2 different ways to graph. So let's start with this guy. Let's graph this guy in blue, and let's use slope and y-intercept. Alright, so we have 3x minus 2y equals negative 4. So let's solve this for y. So we're going to minus the 3x over and then divide by negative 2. So that's going to be positive 3 halves plus 2. So my y-intercept is 2. And then I'm going to go up 3 over 2. Up 3 over 2. I could also go down 3, left 2. I wonder if I have a ruler here. I bet I do. To graph this because, oh, that's too complicated. All right, you guys, why don't you pause the video and see if you can graph this other one. This one might be tough with slope and y-intercept, but see what you can do. You could also try just using the intercepts. All right, so if we solve this for y, we get y equals 3 over 2x minus 1/6. So this is a little weird to graph with a y-intercept of negative 1/6, but I'll just kind of guess that it's right here. And then I'm going to go up 3 over 2 again to 3 over 2. Now what you'll notice is that this line has the same slope as the blue line. So if they have the same slope, that's going to mean that these lines are parallel. And since they're parallel, they are not going to intersect anywhere, which means that there is no xy value that makes both of these equations true. Okay? So if we try to solve this algebraically, something's going to happen that tells us that this system has no solution, and we'll see what that looks like here. Now, when a system has no solution, it is called inconsistent. Inconsistent. Okay, no solution, it's inconsistent. So let's see what happens if we try to solve this algebraically. I'm going to go ahead and erase this work here. So if you need it, write it down. Now, to solve this system algebraically, we could use substitution or elimination, and we had it already solved for y, so we could use substitution, but it had some fractions and junk, and elimination is really smooth here, so let's use elimination. So let's say I want to get my x's to drop out. Well, I would really need this to be a positive 9, so when I add it to this negative 9, it goes to 0. So to make it a positive 9, I'm going to multiply by 3. So I'm going to multiply each of these by 3. All right, and then I'll write the result down here. So let's see, I'd get 9x minus 6y equals negative 12. Okay, so now I'm going to add those two equations together. So if I add these two equations together, the x's are going to drop out. Wonderful, but uh-oh, the y's dropped out too. And I get this statement that 0 equals negative 13. Well, 0 does not equal negative 13. I have no variables. This is an untrue statement, so that tells me that there is no solution. So even without graphing it, without putting it in y equals mx plus b form, if I algebraically try to solve this, I can see that these lines are going to be parallel because the system has no solution. All right. This is the last example I'm going to do on this video, and then I'll do the 3D ones on another video. So we want to do another same thing here. We're going to graph these two lines and see what happens. So go ahead and pause the video and see if you can graph these two lines. All right, so if you solve the first equation for y, you get y equals 2/3 x minus 4/3. And if you solve the second equation for y, you get y equals 2/3 x minus 4/3. So if you graph these two lines, they're going to be the exact same line. Down here I showed another way. You could also do, this is the intercept method. You could just find the x and y intercept. If you let x be 0 and plug that in, you get y equals negative 4/3. If you let y be 0, you get 4x equals 8, so x equals 2, and you can just plot those 2 points and connect them. All right, but so here's our, I'm going to try to do this without a ruler. Here's our blue line, right? Our purple line's exactly the same, right? Because it's the exact same equation. So basically these two lines are right on top of each other. And when that happens, we have what's called a dependent system. So if we think about how we want to write the solutions, we're writing the solutions as what points will work in both of these equations. All right. Well, there's tons of points. There's infinitely many points that will work in both of these equations. Any point that's on this line will work in both equations. It's not fair to say that any point will work, because when I say will work, I mean make the equation true. It's certainly true that if I take this point right here, say -2, +2, that's not a solution because it's not on this line. But any point on this line will work in both of these equations. So the way we write that in set builder notation is we say the set of all x, y, so the set of all ordered pairs such that y equals 2/3 x minus 4/3. So basically this is saying the set of all x, y that make this equation true, which is the set of all points on this line. And sometimes you'll see y is a real number thrown in there. Okay, so here's our solutions, a bunch of ordered pairs, and they have to meet this criteria. They have to be on this line. So it's not, you can't say all real numbers because that's not true. Right? It has to be the points on this line. All right, so that kind of wraps up our two equations with two unknowns. We could, get nice answers like these. If we graph these two lines, they would cross at this point, 5, -3. If I graph these two lines, they're going to cross at the point -1, -4. And we call that consistent. Consistent. All right, they're consistent means they have a solution. And we saw that in this story problem. If they're like this and they don't have a solution, they're called inconsistent. Okay? Then down here we saw if they're the same line, they're dependent. They're the same, they're dependent. These guys up here, when they're different lines, they're consistent and they are independent. Consistent and independent is one solution. Okay? If I'm like this, I'm inconsistent. And if I'm like this, then I'm dependent. Okay? Alright, so hopefully that helps with 2 equations with 2 unknowns, and in the next video we'll go to 3 equations.